How's it going, guys? So I'm going to introduce the derivative today, which is an object of like monumental importance in the class. We'll spend like half of the year talking about derivatives, basically. So what is a derivative? So here's a definition, one definition. I'll wind up giving you lots of different definitions of the derivative that are all equivalent, but here's the first one. Let f of x be a function, then the derivative of f at a point c is the slope of the tangent line at C. At C. Okay, so this is like a graphical definition of the derivative. So just to be clear what that means, let's consider an example. So suppose that your function looks like this. Maybe this is the graph of f. And let's suppose that C is this point right here. What is the derivative of f at C? Well, here's what you do. You look at the point on the graph above C, this point right here, and then you look at the tangent line. Remember, that's the line that like just hits that point, right? But just barely. I suppose it would be something like maybe, I don't know, maybe like this. Okay? It's hard to draw it perfectly, but maybe something like this. So that is the tangent line at that point. The derivative of f at C is the slope of this line. That's the meaning of the derivative at the point C. Notationally, the derivative of f at C is represented by the following symbol. So symbolically, I actually don't know how to spell symbol. I feel like there should only be one L there. Whatever. Symbolically, we denote the derivative at C as f with this little apostrophe of C. So this expression right here, that is how we represent the derivative at C symbolically. And you just put this little apostrophe looking thing here. It's called a prime. Okay, that little apostrophe is called a prime. So this whole expression is often pronounced f prime of C. Okay. All right. So and as far as exactly what f prime of C would be in this particular example, I guess it's whatever the slope of this tangent line is, which is hard to figure out exactly, but it looks like maybe it's 1, or maybe it's like a little steeper than 1, maybe it's like 1.2 or something. Let's have a look at a printed example. Here's another example that I have here. So here's a graph. This is just some new function. Looks like it's some kind of quadratic. And it looks like my C value is 1, right? That's my x value right there. Here's the point on the parabola associated with x equal to 1. And this dotted line here, that's the tangent line. The derivative of f at 1 is just the slope of this tangent line, which because of the grid we can actually figure out pretty well. You can see that the slope of this tangent line is 2, right? Rise of 2, run of 1. So symbolically, what we would say here is that we would say that f prime of 1, that's the derivative of f at 1, that's the slope of the tangent line at 1, is equal to, what was that slope? It was 2, right? So we would say that f prime of 1 is equal to 2. Now, of course, obviously, you can look at f prime at other values. Let's, for example, look at -1. Here's -1 over here. Look at the dot on the graph. Here it is. I don't have a computer-generated tangent line this time, so I have to sort of just do my best at drawing it for myself. Maybe it's something like this. Yeah, that looks pretty good. What is the slope of that line? It looks like it's -2, right, down to over 1. So the derivative of this function at -1 is -2. In symbols, I would write f prime of -1 is equal to -2. Okay, maybe just one more example. Let's look at the derivative of this function at 0. So here's 0. You look at the point on the graph associated with 0. You draw the tangent line. Here it looks like the tangent line is maybe like totally horizontal, right? Like I think the tangent line would look like this. So, okay, so there's the tangent line, more or less, and that looks pretty horizontal. So what's the slope of that line? It's 0. So I think the derivative of f at 0 is 0. In other words, the slope of the tangent line is 0. So the derivative at a point is nothing more than the slope of the tangent line at that point. That's all it is, okay? Okay, so let's move on to some of the exercises in the packet, which you'll be doing, but I want to do some of them with you. So here's a function, and I'm asking you to find places where the derivative is positive. So like, what are the intervals, what are the x values on which the derivative is positive? So here's the thing, the derivative is the slope of the tangent line. So you have to ask yourself, where is the slope of the tangent line positive? You know, for example, right here, the tangent line looks like maybe something like that. Is the slope of that line positive? Yeah. So the derivative is positive there. How about over here? Look at the tangent line. Here it is. Is the slope of that tangent line positive? Yeah. So the derivative is positive there. And then we get to this point right here. The tangent line seems to be totally horizontal. Is the slope of the tangent line positive there? No, it actually seems like it's 0. If we go any further, it looks like the tangent line looks like this. That is a line with negative slope, so the derivative is negative there. So the derivative certainly seems to be positive on this entire region, which I suppose goes from all the way out from -infinity up to, it looks like it switches here. It looks like it switches to being negative right about there at -1.5. So I'll just say, you know, between -infinity and -1.5. Okay, that's where the derivative is positive. But we should ask ourselves, is there anywhere else where the derivative is positive? And the answer is yeah. If you look, it's still negative here, still negative here, but then it looks like the slope of the tangent line is 0 here, and then it looks like the slope of the tangent line becomes positive again, right? So I think that the derivative is positive from here off to +infinity. That looks like +1.5 to me, so I'm going to say and +1.5 out to infinity. So those are the places where the derivative is positive. You might notice that these regions where the derivative is positive are exactly the regions where the function is increasing. That is not an accident. It is a fact that if the derivative is positive, then the function's increasing, which makes sense, right? If the slope of the tangent line is positive, then yeah, the function's going like this. It's going up. It's increasing, right? Okay, let's have a look at B, right? Find the places where the derivative is negative. We've kind of already addressed that. Here it's 0, and then here the slope of the tangent line is negative, still negative, still negative, still negative, and it seems like it's negative right up until here. So it looks like between the values -1.5 and +1.5, that's where the slopes, where the derivative, that is, are negative. Now, of course, if you notice, this region is exactly the region on which the function is decreasing. So that's not an accident either. It turns out that a function will be decreasing exactly when its derivative is negative. So if more precisely, if the derivative is negative on a region, then the function is decreasing on that region. Okay? So so derivative is really about the rate of change of the function, the rate at which it's changing. If the derivative is positive, then it's increasing. If it's a really big positive number, then it's increasing quickly. If the derivative is negative, then the function is decreasing. If it's a really steep negative number, like if it's negative 100, then the function is decreasing very quickly. So the derivative at a point really tells you the rate at which the function is changing at that point. Increasing means the derivative will be positive. Decreasing means the derivative will be negative. All right, I get to C. Where is the derivative increasing? This is a really sort of abstract question. Seems like it should be easy, but it's actually pretty tough to think about conceptually. Where is the derivative increasing? Notice that I am not asking where is the function increasing. The function increases on this interval here and on this interval here. We've already addressed that. But where is the derivative increasing? You have to think about the tangent lines. You have to think about their slopes. The derivative is the slope of the tangent line. So if we have a look, maybe I'll just take this eraser here. Okay, so here's my eraser. And I'm going to imagine it riding like a roller coaster. And what I want you to do is to pay attention to the slope of this eraser. Right now it's positive, less positive. Here it's 0, negative. Okay, so just follow that slope. So right now, okay, the slope is like, I don't know, like 2 maybe or something. It's definitely positive. Now, as I ride the roller coaster, what is happening to that slope? The slope of that tangent line is decreasing, isn't it? Yeah, so the derivative decreased over that interval. As I continue, what's happening to the slope? Oh, look at that. It's decreasing even more. It's becoming more negative, right? But then I want you to notice carefully that right around here, it stops decreasing, right? Like on this region, I would argue that the derivative, the slope of the tangent line, is becoming more and more negative, more and more steeply negative, right? At first it's flat, and then it's more negative, and then it's more negative, and then it's more negative. But right around here, right around 0, it stops becoming more and more steep and starts to go the other way. It starts to go like this, right? So here's the thing. Right at 0, the derivative begins to increase. Why? Because look, right now the slope of the tangent line, the slope of this line right here, is negative. But as I proceed, it becomes less negative, until finally the slope is 0. So it's definitely increasing on that interval. And then as I proceed further, the slope is getting more and more positive. So the slope continues to increase. So the derivative is increasing. So where is the derivative increasing? I would say it's all along this region here. Okay, so that would be from 0 off to positive infinity. Where is the derivative decreasing? We've sort of already addressed this. It looks like from out here, the derivative is already decreasing as soon as you start. Because at first it's quite a steep positive number, like maybe it's 2 or 3 here. But then as you progress, the slope decreases right down to 0 and then continues to decrease. Now it's a negative number. Okay, right here. It looks like the derivative, the slope that is decreasing all the way out from negative infinity up to 0. Okay. Excuse me. So finally, where is the derivative of 0? The derivative is the slope of the tangent line. So asking where is the derivative of 0 is just saying where is the slope of the tangent line 0. In other words, where is the tangent line flat? Where is it horizontal, right? And that's right here, right? The slope is 0, and also right here, the slope of the tangent line is 0. So at those two locations, that would be negative 1.5 and also at positive 1.5. Okay? Cool. All right. Next question. It says, again, referring to the graph above, approximate the derivative of f at each indicated point. And it says, do your best to sketch the tangent line, then approximate its slope. Your answers will be very approximate. I'll just do one of these. Let's look at f prime of negative 2. So how do you approximate the derivative at negative 2? Here's what you do. You go to negative 2 on the x-axis, okay, and you look at the dot on the graph associated with negative 2, and then you do your very best to draw the tangent line. You know, it's going to be approximate, right? Like you just have to do your best to draw the tangent line. To me, it looks like maybe it's something like this. That looks like it's more or less tangent, right? Just crosses that point right there. So this thing, this line that I just drew, that seems to be the tangent line to me. All right? Now the derivative at -2, that's what f prime of -2 means. The derivative at -2 is the slope of that tangent line. So what's the slope of that line? Yeah, it's pretty hard to figure out because this line doesn't really go through any grid points, does it? So you just kind of have to do your best and like kind of wing it. Maybe, you know, I'll start from like here to here or something. It looks like maybe from this point to this point it goes up by 1. And of course it goes over 2. So rise over run is 1/2. It looks like maybe it's 1/2. But again, like it's really approximate, right? Like you're approximating the tangent line. That's something you're just doing your best to draw. And even once you've drawn the tangent line, you are approximating its slope. So like you're really approximating twice, which means that the true value of the derivative at -2 is something that we just don't know. Later on, I'll show you how to get the values of derivatives exactly. But if all you have is a graph, you know, this is the best you can do. Okay? All right, cool. Moving on, I want to talk about the relationship between several concepts, and that is the average rate of change, the instantaneous rate of change, and how those concepts relate to the derivative. But before I do that, I'm going to grab my phone charger because my computer's about to die, so just hang tight for a second. Okay, I've got my charger. I'm plugging it in. I know this is absolutely thrilling television. Well, it's not television, but you know what I mean. All right. So, okay, so I want to talk about, first of all, the average rate of change of a function. This is something you saw, I don't know when, a while back, like freshman year maybe. I'll just give you the formula. So the average rate of change over the interval AB, okay, so the average rate of change of a function over the interval AB is given by the following formula. It's f of b minus f of a over b minus a. This is a formula you gotta know. This is the average rate of change over this interval. It is the average rate at which the function is changing over this interval. If this is a positive number, then the function's increasing. If it's a big positive number, then it's increasing quickly. If it's a negative number, then it's decreasing. If it's a big negative number, then it's decreasing quickly, etc. Okay, so that is the average rate of change. Now, what I want to say is the following. I'm going to give you now a different definition of the derivative. I told you previously that the derivative of a function at a point was the slope of the tangent line at the point, and that's true. I'm now going to give you an alternative definition of the derivative based on limits. And these two definitions, it turns out, are equivalent. They're the same thing. But seeing why takes a little bit of an argument, but I'll just give it to you. So here is the definition of the derivative, the second definition, or a new definition, the limit definition. So this is the limit definition of the derivative at c, okay? F prime of c, which is the derivative of f at c, is equal to the limit as h approaches 0 of f of c plus h minus f of c over h. Okay? This is, I suppose, the real definition of a derivative. So as you can see, the derivative is actually a limit. And this is the whole reason that we study limits, because derivatives are limits, and that's why they're so important. Now, what I want to do is, what do I want to do? Okay, so the fact that this definition is the same as the definition I gave at the beginning of the lesson, the slope of the tangent line definition, that's something I'm going to do tomorrow. I'll prove that this thing is the same thing as the slope of the tangent line. This limit actually gives you the slope of the tangent line, believe it or not. Seeing why requires a little bit of work, but we'll do that tomorrow. For now, just take my word for it. This is the same thing as the definition I gave at the beginning of the lesson. What I want to do is I want to have you think for a moment about driving in a car. Now, suppose that you get into your car, and let's suppose that you drive 60 miles. Okay, so you hop in your car, you drive 60 miles, and you do that in 1 hour. Okay? And then you stop. Cool. Here's the question. How fast did you go? Which is another way of saying, what is your rate of change? Like, asking how fast you went is like saying, how fast did your position change? What was the rate of change of your position? Or if you like, the rate of change of the distance that you traveled. That's what speed is all about. So how fast did you go? Well, you went 60 miles, and you did that in 1 hour, so it looks like you went 60 miles per hour, right? Cool. But here's the thing. If you looked at your speedometer throughout that trip, would it have read 60 miles per hour the entire time? No, probably not. Probably you got into your car, you're pulling out of a driveway or a parking lot, you're going very slow. The speedometer says 5 miles per hour. Then you get onto some side street and you're going 20, and then you get onto the highway and then you're going 65, 70, right? So your actual speed is changing all the time. So here's the question. Here's the idea, I should say. This thing here, this 60 miles per hour thing, that is in fact your average rate of change, right? It's like change in position over change in time. It's basically this thing right here, right? That's what it is. It turns out average rate of change is different from what your speedometer registers. I'm going to pause here. Okay, so as I was saying, the point of this is that this object here is the average rate of change. It's just your total distance divided by your total time. That is different from what your speedometer reads at any given moment, right? So there are really two different notions of rate of change. One is the average rate of change, which is just your total distance over your total time, which, as I said, is essentially this thing right here. And then there's this separate notion of rate of change. It's what your speedometer reads. And that is called the instantaneous rate of change. Okay? Or IROC. So the instantaneous rate of change is the rate at which the object is changing, the rate at which the function is changing, not over an interval, but actually at a single instant, at a single moment in time. That is what your speedometer registers. Now, it turns out that the instantaneous rate of change of a function, okay, so if you have some function f and you want to know what is the instantaneous rate of change of some function f at some point c, it turns out that this is the derivative of f at c. okay? So the instantaneous rate of change of a function at a point, not the average rate of change, not its total rise over total run over some interval, but rather the rate at which the function is changing at a single point, at a single instant. That is actually the derivative of f at c, okay? So just to kind of summarize, I want to emphasize that we now have several different ways of interpreting or understanding the derivative. One is the definition I gave at the beginning of the lesson, that it is the slope of the tangent line. The next is that the derivative is this, this limit expression here. It's this like limit. And then the third interpretation I'm giving you of the derivative at a point is it's the instantaneous rate of change of the function at the point. All those different ways of viewing it are equivalent. They all mean the same thing. Okay, now I want to segue into sort of one final thing. I'd like to talk about the fact, and this is a really key fact, the average rate of change over some interval AB is an approximation of the instantaneous rate of change at any c inside the interval. That's a big idea, okay? So what am I saying? I'm saying you've got some interval, a to b. Pick any point you like, c, inside that interval. And suppose you want to know the instantaneous rate of change at that point. It turns out that if you compute the average rate of change over the entire interval, that will be an approximation of the instantaneous rate of change at the point. And further, the smaller the interval AB is, the better the approximation. Okay? And, just to make this clear, let's return to our example of, the car. If you go 60 miles over 1 hour, that's your average rate of change. In some sense, that is an approximation of how fast you are going in one moment over your trip. It's an approximation of what your speedometer was reading during all the times during your trip. Now, it's a very rough approximation because this is a very large interval. 1 hour is a long time, and you're taking an average over a long period of time. But if you looked at your average rate of change over a much smaller interval, like if you just looked at your average rate of change over, say, a 30-second interval, how far did you go over those 30 seconds divided by 30 seconds? That would be a very good approximation for what your speedometer was reading during that trip. Okay, so the average rate of change over an interval is an approximation of the instantaneous rate of change at c for any point c inside that interval. Furthermore, the smaller the interval, the better the approximation. So there's just one more thing that I want to tell you about how the average rate of change approximates the instantaneous rate of change. And that's the following. It's that the average rate of change over some interval AB approximates C best if C is in the middle of the interval. Okay, like if it's dead in the center. So so just to quickly summarize what's happening, and then we'll do an example, and that'll be it for today. So really quickly, I introduced the derivative, right? And I gave you the derivative. I told you the derivative was the slope. So derivative of f at c, which is represented symbolically as f prime of c, right? That's the symbol for the derivative of f at c. That object is the slope of the tangent line at C. That's the first definition that I gave for you. And we have another way to understand the derivative as the instantaneous rate of change of f at C. That's the idea. Okay, so these three things all mean the same thing. Derivative of f at C, the slope of the tangent line at C, and the instantaneous rate of change of f at C. They all mean exactly the same thing. And what I've shown you just now is that the average rate of change over an interval approximates the instantaneous rate of change at C. In other words, the average rate of change over an interval approximates the slope of the tangent line, or if you like, the derivative. Those all mean the same thing. And of course, the smaller the interval, the better the approximation. And it's best if C is right in the smack dab middle of the interval. All right, so let's just look at the example that I have in the worksheet, which you have a copy of through Canvas. So it says, shown below are some x and y values for some function f. So we don't know the formula for f, we just have some table values, x and y values, and it says approximate the derivative at x equals 3. Of course, derivative means the same thing as the instantaneous rate of change. Now, the idea is that we know that the average rate of change can be used to approximate the instantaneous rate of change, right? So we can use that fact to do this approximation. The only question is, what interval should you use, right? You could compute the average rate of change over any number of intervals, right, in this table, say from 2 to 4 or from 3 to 4 or whatever. Which interval best will give you the best approximation of the instantaneous rate of change of the derivative at x equals 3? Well, two things to consider. Number one, if possible, you want 3 to be in the middle of your interval. Okay? And the other consideration is you want your interval to be as small as possible. So which interval should you use? The answer is you should be using this one, 2.5 to 3.5. Okay? So 3 is right in the middle of that interval, and it is as small as you can make it, right? You could make it bigger, but that would make things worse. So yeah, so let's compute the average rate of change over 2.5 to 3.5. That is going to be, actually we've got the work right here, right? Average rate of change over that interval is going to be f of 3.5 minus f of 2.5 over 3.5 minus 2.5. These are, f evaluated at 3.5 is just the y value associated with 3.5, so that's 12.25. And same idea for f of 2.5. That's just 6.25. So you compute all that and you get 6. So what we can say is that the derivative at 3 is approximately equal to 6. Yeah, so just, so that's about it. What I will say is that today I've given you a definition of the derivative. However, all the methods that you've seen so far are approximate. If you have the graph of a function, then you can approximate the derivative by trying to draw the tangent line and then approximating the slope of that tangent line. That's a very approximate process. Or if you have a table of values, then you can approximate the derivative by looking at the average rate of change over an interval. Those are approximations of the derivative. Very shortly, I will show you how to find the derivative exactly. The real formula for the derivative, the sort of proper definition of it, is a limit. And in fact, that's why we study limits, is because derivatives are limits. All right, so I think that's about it. Just like I sort of said, the review questions or the test review problems for the upcoming test next week are on Canvas, so you should start on those over the weekend. Okay.